Welcome back to ECE 441A, 541A. This is exam week for this particular class. Hopefully, if you're hearing that for the first time, it gives you a few days to get ready. Exam number 2 is on Friday. Before that, you actually have a couple of homework assignments that are due. Today, homework number 4 is due, and homework number 5 is due on Wednesday. In regards to me not being around on Wednesday, I've introduced a couple of new time slots for office hours if that would be of help. Today at 1:30 and tomorrow at 1:30 in the afternoon. Those are special office hours. But Wednesday, we will not have a class meeting. And Friday, obviously, we will be meeting. We will have our exam, our second exam, on Friday. Relative to that, there is practice material for the exam on D2L, and there's also material that should get you ready for homeworks 4 and 5 and exam number 2. I gave you some additional material in lecture video 4.6, which talks about steady state air and system type. The last time we met, we introduced the concept of the Routh-Hurwitz stability criteria, and that's lecture video 5.1. And since then, maybe you've already taken advantage of that, hopefully. There have been some examples of how to apply the Routh array, how you can look at the different cases that leads to or can arise when you're constructing this array of numbers that help us determine not only stability but also some information, additional information on how many roots might be in the right half plane, how many are in the left half plane, and how many are on the imaginary axis. And then there's one more, 5.3, which talks about how can we now use the Routh array to help us design a parameter, a free parameter or a variable parameter in our system. And in particular, we know that the leftmost column in the Routh array, for stability, that needs to be non-negative, and no sign changes. So if that's the case, then you can use that material to help you decide, how do I select this K, maybe for stability, maybe for other purposes. You might want to force imaginary roots for whatever reason. Maybe you're building an oscillator and you want it to shake, your system to shake at a particular frequency. Now, in order to obtain purely imaginary poles, you might look at setting one of the rows to 0. For example, the S1 row in the Routh array, and seeing what that means relative to this flexible parameter, in this case K. Today what I want to do is actually first set the stage for exam number 2, which again is Friday, but also motivate what we will be doing after exam number 2, but we'll do that by reviewing what we've learned to this point, which is helpful, I think, for exam number 2. So today is, in a sense, a review, but a look forward. And hopefully it will be helpful. Hopefully not everyone's head is now on their desk when I said that this is post-exam number 2 concepts, but it will help us put things in context so that it's clear maybe what we've done so far and how we can use that to move beyond where we're at now. Relative to exam number 2, you know the drill. There's 2 sheets of notes that you can create yourself, and you can bring one side copy of table 2.3, which deals with the Laplace transform pairs. You bring that yourself. That won't be provided, and you bring a calculator and something to write with. If you don't have a calculator, you can probably do most of the exam without one, but I wouldn't necessarily show up without one. If you forget one, don't let that throw you into a panic. Just start working as if it's not needed. You won't be allowed your textbook, class notes, computer, cell phone, or a neighbor. Questions on exam number 2? Yes. So what we are covering today is, in a way, a review. So it is material that's consistent with exam number 2. The question was, what we're covering today isn't on exam number 2. May I take a nap? No, that's not the question. But no, I think this is helpful. We're going to see that my calendar starts filling up as we move through the semester, and I'm trying to sort of lay the groundwork so that we can think ahead or plan ahead, and this is one way to do it. So I'm going to try to use this as a review for exam number 2, but also as a look forward. That's the idea of today's class. If you don't follow everything in today's class at the second half, that's not a big deal relative to exam number 2. But the first part you better be very comfortable with, because that is exam number 2 content. And what we're talking about now is the idea of the root locus. You know what roots are. Those are roots of a polynomial. A locus is a pattern. And the root locus is really, how do these poles, and in particular the closed loop poles, how do they move around, how do they migrate on the complex S-plane as you adjust a parameter. And typically it is a gain that we're adjusting. We're usually adjusting a gain k. Or you can think of this root locus as providing a way to create a technique to design controllers if you're now adjusting the gain k. So here's what we've learned so far. We've learned how to model systems via differential equations, transfer functions, etc. You might end up with some plant g of s that looks like this. It's a ratio of factors. The denominator factors represent our open loop poles. We might refer to those as little d of s as a polynomial. And if you multiplied that out, you would have a quadratic. It's s squared plus 6s plus 5. So that might be staring you in the face, and it might not be in factored form. But you want to start getting comfortable with thinking about numerator and denominator factors, and what do those, or how do they play into this idea of roots actually moving around in the complex S-plane. But there is what we've had on, let's say, exam number 1. Now we've moved into exam number 2 material, and in particular, one of the parts of exam number 2 is concerned with design specifications. Design specifications, we've been focusing on 3 that are transient, and then we've also been talking about steady state error. But when I speak of transient design specs, if I say settling time or T sub s, what should be, I hope, coming to mind, or what are you starting to see visually relative to the complex S-plane when I say settling time? I see some hand movements. Hopefully I see some, I can't see the neuron activity in your brain, but hopefully there's something, a pattern, that you're seeing a vertical line and you're adjusting that vertical line. If you push that vertical line to the left, you're making your system faster or slower? Faster. As you push your poles in further into the left half plane, you are producing e to the minus 10t versus e to the minus 2t. And e to the minus 10t is decaying much more rapidly than e to the minus 2t, for example. If I now say peak time, what are you seeing in your mind on the S-plane? If I say peak time, And again, I might see hands, but now you have a horizontal line, and that's now floating above the real axis. And how far it is away from the real axis gives you a larger omega sub d, and with a larger omega sub d, what does that provide? A smaller or larger peak time. Time to peak is pi over omega sub d. Omega sub d is inversely related to the peak time, so you want a small peak time, then that means you want a bigger omega sub d. You want that horizontal line to be further away from the real line in terms of its horizontal location. Then I can mention percent overshoot. Now everybody's thinking pie or pizza, right? That's what that's kind of what I think of when I have this wedge, angles, theta. And if you want less overshoot, what do you want with respect to that wedge? If you want less overshoot, you're going to get less pi, right? You're going to get less pizza. You're going to lower that angle theta. That theta is going to get closer to the real line. It's going to be smaller. This is the picture that you might be thinking of relative to the complex S-plane for transient performance specifications. Settling time, vertical. Peak time, horizontal. Percent overshoot, angle. And really what you want to do, if somebody starts giving you specifications, what you want to be doing is locating maybe the extremes, but don't be picking a particular spec until you've seen all three and how they play together. And on the exam, I could say, I want a percent overshoot bigger than a certain amount. Now what are you concerned about in terms of your dominant poles? Where do you want them to live or lie? Below or above the red line? If I want a bigger percent overshoot, or a percent overshoot more than a given amount, now I want above that red line. If I say I want a settling time bigger, heaven forbid, bigger than some value, now what are you looking at? Now you're looking at those poles being to the right of some vertical line. And what you are wanting to do now is start to think, how do I shade these different specifications, and where is the overlap or the intersection of those shaded regions? So if you want, I didn't say that this was allowed, but you can bring in multicolored pencils if that would help you, so that you can now shade maybe the settling time in blue. Maybe you shade the percent overshoot in red and the peak time in green, and now you see where you have all three regions intersecting. Question? So can you have an impossible percent overshoot? Are you meaning, well, these specifications are for pure two-pole systems, but you can have a very, very large percent overshoot in reality. But typically, what's a sweet spot for percent overshoot? Have we talked about? Have we talked about the optimal size of that pizza or pie wedge? Have we talked about a nominally pretty good value for theta? 45 degrees is sort of a nice trade-off on theta, and that gives you a 5% overshoot, which isn't a lot of overshoot, and it gets you there quite quickly. So if somebody doesn't tell you a specification, you might say, oh, I'm going to maybe try for 45 degrees. Now, here's something into the future. On the exam, you're focusing on a pure two-pole system. In the future, we'll start putting zeros in there, and that throws things off. You put a zero factor in there, and that makes your percent overshoot larger yet. And so that means you probably are wanting to squeeze or pinch those poles into a smaller wedge if you now have finite zeros that are in the same general area as your dominant poles. Those zeros dramatically change your percent overshoot characteristics. Just saying. But for now, for this exam, you're focused on a pure two-pole system which says just poles, no zeros. Is that clear? What else do we have in terms of performance? We have steady state accuracy. And there's a trade-off between your transient behavior and how your system is behaving in steady state. You may tolerate a slower approach to your final values if that produces a much smaller steady state error. And steady state error is connected with system type. Is it clear what I mean by system type? If you have the, I didn't know what color I was going to have. If you have some closed loop block diagram such as this, G sub C, G, their combination, you're looking for how many poles in that combination are right at the origin to determine percent overshoot. To determine system type. Hopefully you're wider awake on Friday morning. So system type is determined by the number of poles you have at the origin in G sub C, G, that combination. That's where we're taking or looking at the number of open loop poles at the origin. Or what does that really correspond to? Pure integrators in that forward path in the time domain. That helps you with steady state accuracy, but now if you have a high system type, that means you have a lot of poles where? Right at the origin. Where is the origin relative to stability? Ooh, it's right on the boundary. So I hope you can appreciate that you're plopping a bunch of poles at the origin to try to make your steady state accuracy better, but now you're making your problem of stabilizing the system more challenging, or the transient behavior, because you've now located a lot of open loop poles right on this boundary, stability boundary. That's helped you for accuracy in the steady state, but it's maybe made it more difficult to achieve the transient behavior that you were looking for. There's that trade-off. We've also talked about the Routh-Hurwitz criteria. Hurwitz is necessary. When is it also sufficient? Hurwitz. For what order of a polynomial? Second and first, right? So first, as long as you have your coefficients are present and positive for a first and second order, then that Hurwitz test is sufficient for stability. Otherwise, you need more information. You can't just say, oh, everything's good because all of my coefficients are there and they're positive and I have a fifth order. You're out of luck. You may actually have some unfortunate locations for those poles. So you need the Routh array. You construct that and you look at how many sign changes. If it's just stability you're after, you don't want any sign changes in that leftmost column of the Routh array. Now, what if we want to put all of these pieces together? We have modeling, we have performance, we have stability. Now what do we do? Well, that's where we're headed. But here's an example, let's say from exam number 2. Suppose now we say we want a 2% settling time less than 1 second. Well, you know the drill. You know T sub s, the settling time for a what? For a 2-pole system. Here we're assuming that the 2 poles that we're focused on are dominating our behavior. So if you had a 10th order system, you're going to focus on the 2 dominant poles, which are, if I have 10 poles spread out on the complex S-plane and they're all stable, that means they're all where? In the left half plane. Now what are the dominant poles? They're the ones that are the closest to the origin. So you start drawing targets or overlapping circles, and you're looking for the smallest circle that contains the first 2 poles. Those are your dominant poles. In our case, let's say that we want a settling time less than 1 second. We can now translate that into a value of sigma. Sigma, now we want our poles to lie to the left of -4. Sigma is equal to 4 at the boundary of that 2% settling time, roughly. We know that it's 1.83, whatever, but we're rounding it to 2%, so this is approximate, but that gives us a good feel for where we want our poles to live. And you can see, if this is now our plant, G of S, with a 0, that's the open circle at -10. We have a 0, a finite 0 at -10. We have a pole at -1, and we have another pole at -5. You can see that those 2 poles do not live to the left of that vertical line at -4. So you can already expect that we're not going to, in the open loop, be able to satisfy that settling time specification for this uncontrolled open loop system G of S. But you have enough skills to be able to analyze that or demonstrate that on an interview. You could say, here, let me demonstrate how to show that this does not give us the settling time specification that we want, which was 1 second. So we say, well, your interviewer goes, well, adjust K. Just make K whatever you want. And can that help you? That's not, K now can influence the 0 or the numerator in the open loop, but it's not adjusting those poles at all, is it? Those poles are stuck at -1 and -5. You have open loop zeros, N of S, determined by the values of S that cause that numerator to vanish. That's S equal to -10. There's one of our zeros. We only have 1 finite 0. And we have 2 poles. 2 values of S. One S is at -1. One S is at -5. That force that denominator, that D of S, to vanish. Those are our open loop poles, are determined from the roots or values of S that cause it to vanish. Our input-output system behavior is determined by, so here, don't you wish I would give you an exam question that says find the transfer function between Y of S and R of S? Well, if I don't tell you what Y of S is, then you might be stumped, but let's say there's Y of S. That would be a gift if I gave you that question, correct? And you'd be going, I must be doing something wrong. He can't ask it that simple. Well, maybe he wasn't quite awake when he designed the exam, so I'm going to just keep going. If I ask you for the transfer function between the reference input R and the output Y, you know how to create that. That's just K times G of S. There's our transfer function. Now if I say, let's hit this system with a constant input. Let's just apply 2,000 counts in the lab. That's what we did. Or you could say, let me put in 2 volts. Or let me put in a position of 10 centimeters. Whatever your system is, now you want that to be constant. If R of t is A, whatever A represents, then its Laplace transform is A over S. We can use that now to find an expression for capital Y of S. And if you're demonstrating your electrical and computer engineering talents to your interviewer, you can say, well, I can do a partial fraction expansion of that. Right? To find the structural form for little y of t. You have y of s, that's in the frequency domain. So that was in the kitchen. Now you want to go to the living room and work in the time domain. You say, oh, I can tell you what that's going to look like, y of t in the time domain, by doing the partial fraction expansion. And you all should be able to find those alphas. Alpha 1, multiply everything by s, set s equal to 0, and boom, you have alpha 1. Alpha 2, etc. On an exam, if I say, what's the structure of y of t? You could just write it down this way and not have to solve for alpha 1, alpha 2, alpha 3. Now you don't have to worry about your calculator or leaving it at home. You just say, oh, the structure of y of t is now a constant alpha 1 plus alpha 2 weighting e to the minus t, and alpha 3 weighting e to the minus 5t. You have 2 transient modes, e to the minus t and e to the minus 5t. Do those surprise you, those modes? Did that catch you by complete surprise that you had an e to the minus t and an e to the minus 5t in your answer for y of t? Why not? You had open loop poles sitting at -1 and -5. Those are giving you your modes in your open loop response. That pole at -1, boom, there's a mode, e to the minus t. That pole at -5, boom, there's a mode at e to the minus 5t. And the constant that you kick the system with from the input, that gets scaled and adjusted to give you an alpha sub 1. You can tell then from that structure, without finding the alphas, information about your settling time. You can now conclude that, oh, I'm not going to reach my settling time in 1 second because of that slowest time constant, tau sub s. That was associated with sigma of the pole at -1. The sigma for that pole at -1 is 1. So we have a one time constant of 1. We have another time constant of 200 milliseconds, or 0.2 seconds. That's the fastest time constant. So if we just had that pole at -5, we would be okay. We would settle in less than a second. But that's not the case. We had 2 poles, and one of those was to the right of that vertical line at 4, and that didn't give us what we needed. And now you could even sketch the transient behavior of your response and show that if you wanted a settling time of 4 seconds, oh, I'm sorry. You can now show that for this particular system, you actually have a settling time of 4 seconds because that's 4 times your slowest time constant. And you're approaching alpha 1. So you're roughly at alpha 1 after an infinite amount of time, and in this case, what's an infinite amount of time? for tau if you're worried about 2%, getting to within 2% of where you want to end up or will end up. And here's just a picture of dominant poles. I've tried to circle those with, or highlight those in yellow, and the blue highlight is just telling you relative to the green highlight that the blue lines are shorter than the green line. They're closer in terms of their distance away from the origin. Those are the closest to the origin. In this case, you have 7 poles. And the dominant ones that we're assuming are what we focus on in this class are the ones that are closest to the origin. If that's the case, if we didn't meet our spec, well, now you know that maybe we want to apply feedback. We need to change the dynamic behavior of the system, and we can do that by closing the loop. We can introduce feedback. Now, if somebody says, oh, give me the closed loop transfer function, you just pull out cheer 2, right? That's just G over 1 plus GH, and you have to realize what is G and what is H. In this case, what is H? 1. And G is really K times G in this case. And now you're hoping that in this configuration, by adjusting K, we can move those closed loop poles from where they were in the open loop. That's the whole point. We want to now adjust K to give us a good response relative to maybe meeting specifications. Those specifications could be performance, transient, and they could be accuracy. But now that we have kg over 1 plus kg, and if we parameterize g as n over d as a ratio of polynomials, then we get a common denominator in the numerator and denominator, and you can see what's living in the denominator. And that is what influences our closed loop behavior. Our closed loop denominator is now some mix of the open loop pole polynomial d of s and the open loop numerator polynomial, and we're making that mix through k. K now, as we adjust k, that starts manipulating the closed loop poles. That adjusts the roots that occur in that denominator polynomial by adjusting just one parameter k. But it depends, obviously, on where we started, which was the open loop pole factors and the open loop zero factors. It's d plus k n of s. And I hope you can see from this slide where that comes from. And now that's what we're going to be playing with after exam number 2, is this d plus k n. And you're going, well, I've got that. Give me exam number 3. I'll take it today. That's true. But now what we want to do is figure out how, by adjusting k from 0 to infinity, we can now plot the entire locus of points that correspond to the roots of that closed loop transfer function. Where are the closed loop poles? If I adjust k from 0 to infinity, where do they live on the complex plane? And when we say locus, that's sort of telling you it's not the entire plane that they are able to touch. They're moving around in a certain way in the complex plane. And obviously it's going to be influenced by d and n. And that's what I'm trying to say here. The closed loop poles are governed by the roots of this denominator polynomial, and we find the roots by setting d plus kn equal to 0, and what values of s satisfy that. So for a fixed k, we're going to have a fixed set of s's. I give you a k, and you holler back, and you scream what the roots are. I give you another k, and you holler back, and you give me the other set of roots. What we want to do now, after exam 2, is learn how to just give a k and get all these different patterns, or these different locations for the poles. And what we want to do then is examine this locus of points as k goes from 0 to infinity. And that's the root locus. That's the locus of these closed loop roots or closed loop poles. Yes? Can k be complex? We are going to allow k to be 0 as a real scalar parameter. And in this class, we're just going to focus on letting k be positive. You could change the sign of k effectively by using positive feedback. So we're using negative feedback, and we're going to keep k living from 0 to infinity, and it will only be allowed to be real. If you made it or allowed it to be complex, how are you going to do that in your system? So now your boss says, I want you to implement this control system and build your controller with a computer. And you go, well, I'm going to create a complex k. And your boss is going, okay, good luck. Don't spend too much time with that. Come back when you have the right answer. Just saying. So in math, yes, it could be complex. But in reality, we have to deal with real coefficients. Now the roots could be complex. That's fine. But k, we're living with it being 0 to infinity and positive. So let's look at now what happens to this d plus kn polynomial when we don't have feedback, when we just put an input in at u and see what shakes at the output y. If k is 0, there's no feedback, and where are our closed loop poles? If we set k equal to 0 and find the values of s that satisfy d plus kn equal to s, what are the roots of s, or what are the roots of that polynomial? Are they related to d or n in any way? If k is 0 with no feedback. Hopefully you can see that if I fix k equal to 0, am I still red? If that's 0, I've annihilated the numerator factor as having any role in the roots of that closed loop pole polynomial. So my closed loop poles are actually my open loop poles because I don't have any feedback. K is equal to 0. So at k equal to 0, we're starting at the open loop poles with our locus. Our root locus is starting on the open loop poles. So let's just play with k. We have all day. We can go to infinity, right, with k. And we'll go in increments of 1/2. Did anybody pack a lunch? Or maybe a breakfast if we're getting a later start? We might be here a while if we go in increments of 1/2 up to infinity. Just be patient. We'll get there. So now, with k equal to 1/2, do you see how that plays into this values of s that cause that polynomial to vanish? Did we change the order of our polynomial? We started with our poles. We had 2 poles. How many poles do we now have with k equal to 1/2? Well, let's keep going, coach. We now have k equal to 1/2. If we multiply d of s, that's s squared plus 6s plus 5. Then we add on 1/2 times the numerator polynomial, or that's 1/2 s plus 5. That now mixes things up a little bit, and now we have a quadratic that's s squared plus 6.5s plus 10. And I'm sure you instantly factored that and found that you now have poles at -4 and -2.5 with a gain of 1/2. Is that better in terms of settling time relative to the open loop? What was the dominant pole in the open loop? What was its location? What was the dominant pole in the open loop? -1, wasn't it? What's the dominant pole here? What's the pole that's closest to the origin? -2.5. Is that faster than a pole at -1? We have sped up the system, haven't we, by introducing feedback and introducing a gain. Now our closed loop poles have actually started to move together. Here's what we had in blue is what we had in the open loop. In red is where our closed loop poles are for k equal to 1/2. So those triangles now are representing how our closed loop poles migrate or move around or form a locus in the complex S-plane as we adjust k. We started at -1 and -5, and now with a k just of 1/2, if we turn this dial from 0 up to infinity, and we've only adjusted it up to 1/2, we've now moved those poles to -2.5 and -4. Well, this is kind of fun, and we're going in increments of 1/2, so the next one is k equal to 1. If k is equal to 1, you see how we can do that. We still have s squared plus 6s plus 5, but now we add in s plus 10. And again, we've changed that quadratic, but we still just have 2 poles. We had 2 open loop poles. We have 2 closed loop poles. We haven't changed the number of poles magically because we're playing with real k's. So now we have poles where? Do you recognize this factored form? If you don't, hopefully you will by next week. Where are the poles located in this factored form? What's the real part of our poles? They're at -3.5. And the imaginary part? They're at 1.6. So the poles are actually, if you've tried to factor this or solve for s, you would find s is going to be complex, and it's going to be in conjugate pairs, and you're going to have poles at -3.5 plus and minus j 1.658. What's the angle? What's theta? So now you need to be thinking about thetas, settling time, peak time. What's omega sub b? It's screaming at us, isn't it? It's 1.658. What's sigma? 3.5. What's the angle? Is the angle bigger than 45 degrees or less than 45 degrees? Our horizontal distance is bigger than our vertical distance, so we're actually less than 45. So we'll have less than 5% overshoot. We'll have a peak time determined by 1.658. And so now our triangles have, boom, they've popped off the real axis, even with a k that's real. And now they've both shifted over, and they're complex conjugates, they have the same real part. They're at minus 3.5. We're almost at our settling time spec, aren't we? For a K of 1. We needed those real parts to be at minus 4, and they're at minus 3.5. Hell, this is so fun. Oh my goodness, I skipped over an interval. Oh, I know you're disappointed, but now I went from 1 to 2 instead of 3, 1.5. So now at 2 for K, we can find that where are we at now? Now we're at minus 4 plus and minus J3. Yay! For a K of 2, we've now reached our settling time spec. Right? What's our percent overshoot? Is it bigger or less than 5%? Can you tell from this information? What's 5% overshoot? What size pizza? What's a 5% overshoot correspond to in terms of angle? 45 degrees. What's the angle associated with minus 4 plus J3? Less than 45. Minus 4 plus J4 would be 45. We're just J3, aren't we? So we're less than 45 degrees. We have less than 5% overshoot. And our poles now are there. We still just have 2 poles, 2 triangles. We started with 2 poles, 2 x's. We better not have increased the number of poles if all we're doing is adjusting a gain K. Well, I must have just stopped at 2. I've met my performance spec. But you can see, well, do you see what's happening? Have you been able to put those triangles, move those triangles in your mind? Maybe not. So let me help you. This is what they've started to do. They stayed on the real line until they reached a particular value of K, and then they popped off and became complex conjugates, and then they started bending over and moving into the left half plane. Further into the left half plane as I adjusted that knob K bigger and bigger. And for those that have already had another class, maybe in control, you could have anticipated this shape. This now you could actually, after exam 2, you might want to go out and buy a set of dividers and a compass, etc., so you can draw the, no, I'm teasing, but you can start creating some interesting patterns of loci. Here we have actually 2 poles, so the triangles live on those red lines. That's the root locus for this particular system. This is the only place that you could possibly live with your closed loop poles for that particular system if you're using just a scalar gain K. If you haven't introduced any other controller except a gain adjustment, now you can live on that red set of red lines, which really is 2 branches of the root locus. We have 1 branch that is here, and then it doesn't really matter whether it goes up or down. Let's just say it goes up, and it moves around, and then it meets, and then maybe it goes to the 0. The other branch comes in, goes down, and it meets, but it can't stay together. So one goes off to minus infinity as we crank up the gain K. The other one goes to, where was that 0 located? At minus 10. But if you have a pattern like this, 2 poles to the right of 1, 0, you know it's going to have that kind of a shape. That it will have, and we'll start using some of this terminology. We'll say that we start, where did our root locus start on the X's, on the open loop poles. It then moves, it stays on the on the real line, and then it breaks away. There's a breakaway point for a given value of K. Then it comes around and it re-enters the real axis. So we have breakaway and re-entry. And then we have one pole that goes to the 0 at minus 10, another one that goes to minus infinity. As we adjust the gain K, we'll have all of this excitement after exam number 2, but you now, hopefully, exam number 2, you're ready for or will be by Friday. Good luck.